Have you ever felt like reality is off? Like something about the universe doesn't quite make sense? You wake up every morning, go about your day, and assume everything around you is exactly as it appears. The sky is blue. Time moves forward. The stars are just distant balls of fire. But what if I told you that the universe as you know it does not exist? We assume that space, time, and motion are constants, unchanging, and predictable. But what if time isn't what we think it is? What if space has a shape we cannot comprehend? And what if the ultimate speed limit of reality is just an illusion? For centuries, humans have tried to map out the universe using complex equations and grand theories. Yet, the greatest breakthroughs, the ones that reshaped our understanding of existence, came from shockingly simple ideas. So, if the fundamental truths of the universe are simple, what if the biggest truth of all has been hiding in plain sight? What is time? Is it just a measurement or something much deeper? What is the true shape of space? Is the universe infinite, or does it loop back on itself? Why does reality have a speed limit? Is the speed of light truly a fundamental rule, or just a side effect of something bigger? These aren't just theoretical puzzles. They define the nature of existence itself. And once you see the answers, you might never look at the universe the same way again. What is time? We live by it, measure it, count it. Time flows forward, never backward. But why? We experience time as a constant, an unbreakable force. But is it truly real? Unlike the air we breathe or the ground we stand on, time has no physical form. You can't touch it, you can't see it, but you can feel its effects. Every second we move forward. Every moment that passes is lost forever. Why does time only move in one direction? If space can be bent, twisted, and stretched, could time be the same? Ancient philosophers believed time was a river, flowing endlessly forward. But modern science suggests it's far stranger than that. Einstein proved that time is not absolute. It bends, slows, and even stops, depending on where you are and how fast you move. Near a black hole, time itself slows to a crawl. If you fell in, the outside universe would speed past you in an instant. But here's the real question. If time can bend and slow, why can't it reverse? Every law of physics allows time to flow either way. Yet, we only move forward. Why? Some scientists believe the answer lies in entropy, the universe's tendency to move from order to chaos. Once something is broken, it doesn't fix itself. Time is not what we think it is. Time follows the same rule, always increasing in disorder. For centuries, we believed time was absolute, flowing the same way for everyone, everywhere. Sir Isaac Newton described time as absolute and unchanging, like a universal clock, ticking at a fixed rate. And for most of human history, this idea made sense. Time felt constant, measured by the rising and setting of the sun. But then, in the early 1900s, one man changed everything: Albert Einstein. Einstein discovered something extraordinary. Time is relative. It can slow down, speed up, even stop, depending on where you are and how fast you're moving. Imagine two people, one on Earth and one traveling through space at nearly the speed of light. Their experience of time would be completely different. The person on Earth might age 10 years, but for the astronaut, only a few months may have passed. This is time dilation. The stronger the gravity, the slower time moves. Near a black hole, time almost stops. If you watched someone falling in, they would appear frozen in time. This is not just theory. In 1971, scientists placed atomic clocks on airplanes and flew them around the world. When compared to clocks on the ground, they were out of sync. Even today, GPS satellites must correct their clocks for time dilation. If not, our GPS systems would be off by miles every day. So time isn't fixed. It stretches, it bends, it flows differently depending on speed and gravity. But here's a mind-blowing thought. What happens if you go faster than light? Would time reverse? This brings us to a bigger question. Could time be a dimension we've yet to fully understand? We live in 3 dimensions: length, width, height. These are the fundamental ways we experience space. But what if there's a 4th? For most of history, we thought time was separate from space, a ticking clock, moving forward, never stopping. But what if time isn't just a measurement? What if it's an actual dimension, just like the space around us? Imagine a world with only 2 dimensions, a flat plane where up and down do not exist. To a 2D being, the 3rd dimension would be invisible, just like the 4th dimension is to us. Now, what if time works the same way? What if we are trapped in a single slice of time, unable to move freely, just as a 2D being cannot step into the 3rd dimension? Einstein's theory of relativity changed everything. It revealed that time and space are woven together into one fabric, a continuum we call space-time. As you move faster, space contracts and time slows down. The most extreme example? Black holes. Near a black hole, gravity distorts space-time so dramatically that time nearly stops. But if time is just another dimension, could we move through it the way we move through space? In theory, nothing in physics forbids time travel. Yet, we only experience time in one direction. Why? Entropy. The universe naturally moves from order to disorder. A shattered cup never reforms on its own. Some physicists believe time's one-way flow is a property of the universe itself. But what if there's more to the story? If time is truly a dimension, could we one day find a way to navigate it? The answer could change everything we think we know about reality. Look up at the night sky, stars stretching endlessly in all directions. But is that really the case? Is the universe infinite? We live in a world where almost everything has limits. A road has an endpoint. A planet has a surface. But what about the universe? For centuries, philosophers and scientists have asked this question. If you traveled infinitely far, would you ever reach an edge, or would space continue forever? In ancient times, many believed the universe was a finite dome, a celestial sphere enclosing the Earth. But today, our telescopes show something far more complex. The farther we look, the more galaxies we find. No walls, no boundaries, just endless cosmic structures stretching in all directions. But here's the paradox. Infinity is not a number. It's an idea, something without limit. So, if the universe is infinite, does that mean it contains everything? Imagine looking far enough into space and seeing a copy of your own galaxy, or even a copy of yourself. If the universe is truly infinite, then statistically, somewhere out there, an identical version of you may exist. A person with the same thoughts, the same memories. But there's a problem. While the universe may be infinite, the part we can observe is not. The universe has existed for 13.8 billion years. Light from distant galaxies has only had that long to reach us. So no matter how powerful our telescopes become, we can never see beyond a certain point. And even if we could travel faster than light, would we ever reach a wall? Or would we just find more space? More galaxies? More universes? Some scientists suggest that space might be finite but unbounded, like the surface of a sphere. You could travel forever, but eventually you'd loop back to where you started. But here's where things get even stranger. The universe is not just vast, it's expanding. The further a galaxy is from us, the faster it moves away. This raises a crucial question. If space is infinite, how can it still be expanding? Our observations suggest that the universe may be infinite, but we can only see a small fraction of it. So what lies beyond our cosmic horizon? More of the same? Or something different? The answer to this question shapes everything we think we know about the cosmos. And to understand it, we must explore the true shape of the universe. If the universe is infinite, does it have a shape? Or is it simply endless in all directions? Scientists believe the universe must have an overall structure. But what does that structure look like? To understand this, physicists have proposed three possible shapes: flat, spherical, and hyperbolic. These models are based on general relativity, which tells us that space itself can be curved by gravity. 1. The flat universe. In this model, space has no curvature. Parallel lines remain parallel forever. If the universe is perfectly flat, it means space extends infinitely in all directions and never loops back on itself. Observations from the cosmic microwave background suggest that our universe is very close to being flat. But is it truly flat, or just almost flat on a cosmic scale? 2. The spherical universe. In this model, space curves in on itself, like the surface of a massive sphere. If you traveled far enough in one direction, you wouldn't reach an edge. You would loop back to where you started. In a spherical universe, space is finite but unbounded. You could keep moving forever, but you'd always return home. This model suggests that the universe may one day collapse back on itself due to gravity, leading to a big crunch. 3. The hyperbolic universe. The opposite of a sphere. Space curves outward, creating a saddle-like shape. In a hyperbolic universe, parallel lines eventually diverge. Space stretches outwards, expanding faster the further you go. This would mean the universe is infinite, expanding forever, never looping back on itself. So which model is correct? Flat, spherical, or hyperbolic? Observations suggest our universe is very close to flat, but not perfectly so. But if space is mostly flat, what about its edges? Could there be an end? Or does it curve in ways we cannot yet perceive? To truly understand the shape of space, we need to look beyond galaxies, beyond the cosmic web, into the very nature of gravity itself. And nothing distorts space quite like black holes. To truly grasp how space bends, we must understand what happens when it collapses into darkness. Space bends, time distorts, and at the heart of it all lies a mystery we still struggle to understand. Black holes, regions of space where gravity is so strong, not even light can escape. Einstein predicted their existence over a century ago, but only recently have we been able to see them. In 2019, the Event Horizon Telescope captured the first-ever image of a black hole, a dark shadow surrounded by a ring of glowing light. Black holes don't just warp space, they warp time itself. The closer you get, the slower time moves. To an outside observer, an object falling into a black hole appears to slow down, almost frozen in time. But from the object's perspective, time flows normally. But fall too close, and the difference in gravity between your head and feet becomes unbearable. A process scientists call spaghettification. Anything crossing the event horizon is lost forever. Or is it? Stephen Hawking proposed that black holes aren't completely black. They might slowly evaporate, releasing what we now call Hawking radiation. If true, this means black holes don't last forever. They slowly fade, leaving behind only a whisper of their existence. But what if you could escape? What happens to information that falls into a black hole? Does it disappear, or is it somehow preserved? Some theories suggest black holes could be gateways to other parts of the universe, or even to parallel universes. But so far, we have no way to test this idea. What we do know is that black holes reshape the space around them. They prove that space is not a flat, empty void, but a dynamic, ever-changing fabric. And they are not alone. Throughout the cosmos, space is constantly stretching, bending, and warping in ways we are only beginning to understand. If we truly want to understand the shape of space, we must look at more than just black holes. We must consider the hidden forces shaping the universe, forces we still cannot see. And to do that, we must explore the invisible, dark matter, dark energy, and the unseen forces that guide the cosmos. There is a limit to how fast anything can move, a fundamental speed that defines the structure of reality itself. That speed is 299,792,458 meters per second, the speed of light. No matter how advanced our technology, no matter how powerful our engines, we can never exceed this cosmic speed limit. Why? The answer lies in Einstein's theory of relativity, which revealed that space and time are not separate, but part of a single, interconnected fabric. When you move through space, you are also moving through time. And the faster you go, the slower time moves for you. This is called time dilation. A moving object experiences time at a different rate than one at rest. But there's another problem. The faster you go, the harder it is to go even faster. The closer an object gets to light speed, the more energy it takes to keep accelerating. And at 99% the speed of light, the energy needed becomes nearly infinite. This is why even our most powerful particle accelerators, like the Large Hadron Collider, can only push particles close to the speed of light, never beyond it. But why is light different? Why does it move at this ultimate speed, without ever slowing down or speeding up? Unlike other objects, light has no mass. This allows it to always travel at exactly the speed limit of the universe. And here's something even stranger. No matter how fast you move, you will always measure light moving at the same speed. The speed of light is not just a number. It defines the very fabric of reality. It controls how we perceive time, distance, and motion. But what if we could go faster? What would happen if we broke this ultimate speed limit? Some theories suggest that space itself might be the key, that perhaps we don't need to move faster, but instead manipulate the space around us. To understand that, we must look deeper into the nature of space itself, and that means exploring hyperbolic space and motion. Space is not flat. It bends, stretches, and warps. But what if it does more than that? What if space itself has a shape that affects how objects move? Scientists believe the universe might have an inherent curvature, a shape beyond our 3 dimensions. We've explored 3 possible shapes of the universe: flat, spherical, and hyperbolic. But only one of them explains the way objects move at extreme speeds. This is hyperbolic space, a universe where everything moves outward, stretching away exponentially the further you go. But what does this mean for motion? Could this shape explain why there's a speed limit in the universe? In hyperbolic space, the rules of motion change. The faster you go, the more space seems to curve against you. It's as if space itself is resisting acceleration. No matter how much energy you apply, you can never reach the speed of light. This is why motion in hyperbolic space explains the speed limit. The more you push, the more space itself pushes back. This idea aligns perfectly with Einstein's relativity. It's not just that light is fast, it's that space is structured in a way that prevents anything from exceeding light speed. Think of it like Earth's surface. You could walk forever, but you'd always be bound to the shape of the planet. In hyperbolic space, motion is guided by curvature. The faster you go, the more your trajectory bends, preventing you from ever reaching the speed of light. This is why exceeding the speed of light is fundamentally different from simply going faster. Space doesn't allow it, not because of a physical barrier, but because of how motion works in a curved universe. This also explains why the universe expands faster the further away you look. The further galaxies are, the more space stretches between them, making it look like they're accelerating away. This effect is not due to galaxies moving faster. Rather, it's space itself that is stretching, just like in hyperbolic motion. But what if we could use this curvature to our advantage? Instead of fighting against space, could we bend it to go beyond the speed of light? Some scientists believe that the secret to faster-than-light travel isn't acceleration. It's controlling the shape of space itself. To truly understand this, we need to step outside our own perception and see motion from the perspective of light itself. Light moves at the ultimate speed, 299,792,458 meters per second. But what if we could see the universe through the eyes of light itself? From our perspective, it takes years, centuries, or even billions of years for light to reach us. But to a photon, time does not exist. Einstein's relativity tells us that as you move faster, time slows. But at light speed, time stops completely. If you could somehow travel at the speed of light, you would experience no passage of time. Every journey, no matter how far, would feel instantaneous. A photon born in the early universe reaches our telescopes today. But from the photon's point of view, it arrived the very instant it was created. This is the strange reality of light. It doesn't just travel through space, it moves outside of time itself. Unlike anything else in the universe, light has no mass. That single fact allows it to move at this ultimate speed, never slowing, never stopping. This is why information itself is limited by light speed. Every message, every signal, every beam of light, confined to the same cosmic limit. But what if we could defy this limit? What would happen if something could break free from light's constraints? Some theories suggest it might be possible, but the implications are beyond anything we've ever encountered. We live in a universe bound by the speed of light. No information, no object, no force has ever been observed to move faster. But what if something could? Breaking the speed limit of the universe would mean rewriting everything we know about space and time. If we could travel faster than light, we wouldn't just reach distant stars. We might reach the past itself. The equations of relativity suggest that moving faster than light could lead to time paradoxes, events happening before their causes. But some theories suggest a loophole. We don't have to move faster than light. We just have to bend space itself. If such a drive were possible, it would mean traveling to Alpha Centauri in days rather than centuries. The entire universe would open up. But there's a problem. So far, this remains theory. The energy required is beyond anything we can generate. Could there be unknown forces in the universe, dark energy, quantum effects, that allow us to bypass these limits? We don't have the answers yet. But if faster-than-light travel is possible, it won't just change how we move. It will change how we understand reality itself. The universe is vast, beyond comprehension. And yet, for centuries, we have tried to understand it. From Newton to Einstein, from classical mechanics to quantum physics, each breakthrough has rewritten our understanding of reality. We once believed the universe was eternal and unchanging. Then, we discovered it was expanding. That time itself could be stretched, twisted, slowed down. We once thought time was absolute. That space was a passive void. We now know they are connected, a single fabric shaping the motion of everything. Light from the beginning of time is still reaching us. Every photon carries a story, a glimpse into a universe that no longer exists as it once was. And yet, for all we know, there are still gaps in our understanding. Questions science has yet to answer. Why does the universe have a speed limit? Is it truly a barrier, or just a limitation of our perspective? Could there be a way around it? Not by moving faster, but by moving differently. Then, there are the forces we cannot see. Dark matter, dark energy, the unseen world that shapes everything around us. Even at the smallest scales, reality defies intuition. Quantum mechanics tells us that particles can exist in multiple states at once. That reality may not be as fixed as we believe. What else is out there, hidden beyond our current reach? Are there dimensions we cannot yet perceive? Perhaps one day, we will harness the very fabric of space itself, finding ways to travel beyond the limits we now believe to be absolute. Because if history has taught us anything, it is that certainty is an illusion. What seems impossible today may be trivial tomorrow. We are still at the beginning of our journey, a species taking its first steps into the unknown. Every great scientific revolution has shattered what came before. What new revolutions lie ahead? Perhaps the answers are waiting. Perhaps the unseen world is closer than we think. But for all we know, the vast majority of the universe remains a mystery. 85% of the universe is invisible to us. Dark matter, dark energy, forces we can detect, but not yet explain. We barely understand how the universe began, even less about how it might end. And on the smallest scales, quantum physics tells us reality isn't even solid, just probabilities and waves of possibility. What else lies beyond our reach? Are we missing something fundamental about the nature of reality? Perhaps one day, with new physics, new tools, new ideas, we will break through these limits. Maybe the greatest discoveries are still ahead of us. Maybe the unseen world is waiting. And the only way to find out is to keep looking. Narration: we live on a tiny world, orbiting an ordinary star, in an unremarkable corner of the galaxy. And yet, we dare to ask the greatest questions. We are made of the same atoms as the stars. The universe created us, and now we are trying to understand the universe in return. For centuries, we believed we had the answers. We thought we understood space, time, and motion. But time and again, reality has surprised us. Every generation believes they have reached the limits of knowledge. And yet, each new discovery only opens more doors. The universe is not what we once thought. Space is not a void. Time is not absolute. Even the speed of light, once thought to be the ultimate limit, may not be the end of the story. Knowledge is like the ocean, each wave reaching further than the last, but never quite touching the horizon. Our journey is only beginning. There is more to discover, more to explore, more to question. The unseen world is all around us. It shapes our past, our present, and our future. And one day, it will no longer be unseen. The only real limit is how far we are willing to look. If everything we know about the universe has changed before, what makes us think we finally have it right? There was a time when we thought the Earth was the center of everything. A time when we believed space was static, when time was absolute. But each new discovery shattered the illusion of certainty. The cosmos is not what we once thought. The deeper we look, the stranger it becomes. Are the rules we believe in today just another stepping stone? Is there something beyond the speed of light? Beyond space-time itself? What if time is not a straight path, but a landscape waiting to be navigated? What if light is not the ultimate speed, but merely a boundary of our current understanding? Could the next great discovery rewrite reality itself? Will we one day look back at our theories and laugh at how little we understood? And if the universe holds secrets beyond our imagination, are we even asking the right questions? The unseen world surrounds us. It shapes our reality, whether we acknowledge it or not. But perhaps the real question is not what we see, but what we have yet to see. So, what will we discover next?